let's take a look at relativity examples, simultaneity, and spacetime. So when we discuss relativity, it's easy to get bogged down in these abstract ideas of reference frames and relative velocities. And I want to take a moment to discuss a more concrete example. We're going to talk about something that's actually observed, and that's muon decay. So I'm going to draw a picture here. Here's the Earth's surface, here's the atmosphere, and here's space. And the atmosphere is about 10 kilometers thick. Now this, of course, is an oversimplification of the atmosphere. If you talk to a meteorologist, they'll get upset. But this will work for our purposes. So it turns out that at all moments, the Earth is bombarded by cosmic rays. We're not going to worry about the source of these cosmic rays. All that's important is that they're very high energy. So a cosmic ray comes in, it impacts the top of the atmosphere, and this can create a particle called a muon, and the muon will come racing toward the Earth's surface. Now a muon is essentially a very heavy electron, and it's unstable. It has a half-life of about 2.2 microseconds. So just like radioactive nuclei will decay with a half-life, muons behave similarly. So we've got these muons, and they're coming down towards the Earth, and when they're produced, these cosmic rays have high energy, so they give the muon a really high kinetic energy. So consider a muon that's moving at 0.99 the speed of light. In that case, the Lorentz factor for this thing is 7.1. Now, if we observe this from the ground, then we would say, okay, well, if we have something moving at 0.99 c and it's going to travel 10 kilometers through the atmosphere, we would think that it would take 33 microseconds for that muon to reach the ground. Now, 33 microseconds, that's approximately 15 half-lives of a muon. So we can use our radioactive decay equation, and we can find that only 0.003% of the muons should reach the ground, right? If there's 15 half-lives being passed, that's the percentage that would exist after 15 half-lives, right? Well, no, that's not the way it works, because remember, time will move more slowly in the moving reference frame. In the reference frame of the muon, time will pass more slowly. So in the reference frame of the muon, let's think about it. We've got this time dilation equation, and we know the Lorentz factor is about 7.1 for this situation. In the Earth's frame of reference, 33 microseconds pass. But how much time passes in the muon's frame of reference? Well, we can figure that out. Okay? If we do the math, we find that in the muon's frame of reference, as it passes through the atmosphere, only 4.7 microseconds pass. Well, let's see. If the muon experiences about 4.7 microseconds, that's only about 2.1 half-lives. So that means 23% of the muons will reach the ground. Well, that's a much bigger percentage than we thought of over here if we didn't take into account relativistic effects. An alternative way to think about it is not with time dilation, though. It's with length contraction. Because if we consider the muon's perspective, consider the reference frame of the muon. So if we consider the muon to be at rest, then the Earth and the Earth's atmosphere is traveling toward the muon at 0.99 c. So it has a Lorentz factor of about 7.1. So from the muon's perspective, the Earth's atmosphere is moving toward it, and its length is contracted. And we can use the length contraction equation then. Here we go, okay. Well, the proper length of the atmosphere is 10 kilometers. So the observed length from the muon's perspective would be 10 kilometers divided by 7.1, which is 1,410 meters. And moving at 0.99 c, it takes about 4.7 microseconds to move through 1,410 meters. And then we retrieve, okay, well, if it only takes 4.7 microseconds, that's about 2.1 half-lives. And again, 23% reach the ground. Now, this phenomena is observed, and it's one of the pieces of evidence to support the theory of special relativity. Now, another example that we'll look at is the ladder fitting into a barn. So imagine that you have a barn, and the barn is 4 meters wide. And then you have a ladder, and the ladder is 5 meters wide. And you're asked, well, can you fit the ladder in the barn? Well, of course you can. You just have to make the ladder move very fast, and then you'll have length contraction, right? The proper length of the ladder is 5 meters, and you want the ladder to contract to 4 meters. So you can do the math. you need a Lorentz factor of what? 5 meters over 4 meters, 1.25. And so then you can figure out what speed the ladder has to travel, right? Because the Lorentz factor is 1 over the square root of 1 minus v squared over c squared. Lorentz factor is to be 1.25. Okay, solve for that. So the speed has to be 0.6 of the speed of light. Okay, so you can make the ladder fit into the barn as long as the ladder moves at 60% of the speed of light. But wait a minute, because that's from the perspective of someone standing outside of the situation that's in the reference frame of the barn. But from the perspective of the ladder, that doesn't make any sense, right? If you were riding on the ladder, let's say that you're on the ladder as it moves at 60% the speed of light. Well, from your perspective, right, the proper length of the ladder is 5 meters. It's a 5-meter long ladder. What you would see is that the barn would be moving toward you, and the barn would be length contracted. And in fact, you can calculate how wide the barn would be when it's length contracted and you're moving at 60% the speed of light. If that were the case, then let's see, well, you'd have a Lorentz factor of 1.25. So the barn would be not 4 meters wide, it would be 3.2 meters wide. And the ladder definitely wouldn't fit into it. So does the ladder fit in the barn or not? Well, the answer is that from the perspective of an observer that's at rest with respect to the barn, yes, it does fit in the barn. And from the perspective of a person moving with the ladder in the reference frame of the ladder, no, it doesn't fit in the barn. It depends on whose perspective you're thinking about. And that gets us to something called the principle of simultaneity. So events at different locations, which are simultaneous in one reference frame, are not simultaneous in all other reference frames. So for the ladder and barn problem, a person who's at rest with respect to the barn, for that person, one end of the ladder and the other end of the ladder are at the ends of the barn at the same time, simultaneously. But for a person who's at rest with respect to the ladder, who's moving with the ladder in the ladder's reference frame, that doesn't happen. That is not true. And we can think about another example of this. Let's think about a train car that's moving to the right, and there's going to be a person inside of the train car, and then there's a person standing out here, and this person is not moving. So let's say that at the moment that we show right here, 2 bolts of lightning hit either side of this train car. Now the train car is moving to the right at half the speed of light. And there's 3 meters here and 3 meters here. So the person is right there in the middle of the train car. Now, after 5 nanoseconds, the light from the bolts has traveled a little bit. After 5 nanoseconds, the light from each of the bolts has traveled 1.5 meters. But also, the train has traveled to the right, 0.75 meters. So we have a situation like this. Here's the light wave from the blue bolt, here's the light wave from the green bolt. Now after 10 nanoseconds, well, at that point, the light waves have now moved 3 meters, and the light waves have now collided. They're in the same place. And the person who's observing this from rest would see that the 2 bolts had occurred simultaneously. The light from each of those lightning bolts has now reached the person at the same time. So that person would see the 2 lightning bolts as being simultaneous. However, the person in the train, let's think about that. The person in the train, well, they have already seen the green light at this point. The light from the green bolt has already arrived and gone past them. But they have not yet encountered, or not yet received, the light from the blue bolt. So the person in the moving frame, in this moving train, would not see these 2 bolts as being simultaneous. And that's the principle of simultaneity. Events at different locations which are simultaneous in one reference frame are not simultaneous in other reference frames. And now let's look at space-time diagrams, also known as Minkowski diagrams. So we're going to put the vertical axis as time, and in the horizontal axis we're going to have position along one dimension. So we're just going to talk about x. We're not going to do y or z. But if I have an object that has a constant position, then in a space-time diagram, well, constant position, it would look like this, just like that. It stays at the same location at all times. Now, if I have an object that starts at the origin and it drifts to the left over time, then it would look something like that. And if I had an object that started over with a negative position and then moved at a higher velocity, then it might look like this. And I could have another object that starts at the origin but moves quickly in a positive direction, and it would look like that. And at this moment, we would say that those two objects there crossed paths. And in a Minkowski diagram, these lines are called world lines. They're lines showing the position as time passes in a space-time diagram. Now, in the space-time diagrams that we draw, the time axis is going to actually be the speed of light times time, right here. And on the horizontal axis, we're just going to have the dimension x. So if I have a world line for an object, it might look like this. And if the object begins at the origin, then the gradient of the graph would equal ct over x. And I can rearrange that, right? Because that's equal to c times x over t to the -1 power. And x over t is the velocity of the object. So that's equal to c divided by v. That's the gradient. I can also draw in the angle theta right here. And if I were to calculate the tangent of theta, it would equal, what, x divided by ct. And x over t is the velocity, so that's equal to v over c. The tangent of the angle between the world line and a vertical axis in the space-time diagram is equal to v over c. So if I have a faster object, it will have a smaller gradient in this, and it will have a greater value of theta. Now, I can draw many different world lines. Let's look at a few. So, draw a new space-time diagram. If I have a line with a gradient equal to 1 in a space-time diagram, well, that means that the object is moving at the speed of light. So that would be the world line for a photon, for example. All these world lines right here that are sort of at an angle smaller than that of a photon, these are just objects that are moving at less than the speed of light. And the lower the velocity is, the closer it is to being vertical. Now, if I draw a line right here, that object, that world line, represents an object moving faster than the speed of light. So that's not allowed. We haven't formally discussed it, but it turns out that objects cannot move faster than the speed of light, so that world line is impossible. Another thing that we can do with space-time diagrams is we can overlay the axes for a moving reference frame. And I'll show you what I mean. Let's draw our regular space-time diagram. But then let's think about drawing axes for a moving reference frame on top of the axes that we already have. So we have ct and x, our usual axes and our usual reference frame. But if we have a moving reference frame, then the axes for that reference frame would look like this, ct prime and x prime. Notice that the two axes for the moving reference frame are offset from our regular axes by angles theta, and they are bisected by that 1-to-1 line, the world line of a photon coming from the origin. Now, this looks a little bit confusing, and it's a little difficult to interpret. It takes some time. But I want to point something out. When we draw it this way, if I were to draw the coordinate system for the ct prime and x prime axes, they would be distorted. The lines of constant x prime would be parallel to the ct prime axis, and the lines of constant ct prime would be parallel to the x prime axis. And it turns out that those axes are also stretched so that a meter along the x-axis has a different length than a meter along the x prime axis. And the last thing that we're going to look at is something called the space-time interval. So we've seen that distances and lengths in space and intervals in time are not the same in different reference frames. These are not invariant in different reference frames. But there is an invariant quantity across all reference frames, and that's called the space-time interval, and it's represented with a delta S. And the mathematical definition of the space-time interval is that the space-time interval squared is equal to c times the time interval squared minus the space interval squared. So this space-time interval, again, is invariant. It's the same in all reference frames. Another way to think about it is that the space-time interval squared is equal to the separation in time squared minus the separation in space squared. So again, this quantity is special because it is invariant across all reference frame. An observer in any reference frame would agree on the length of the space-time interval. And though I say length of the space-time interval, I want to point out, or I want to emphasize, that the space-time interval is not a length in space. It's not a length in time. It's a length in space and time. And that mixing of space and time together into a single thing is one of the hallmarks of special relativity. And I'll leave you with a quote from Hermann Minkowski from his original paper called Space and Time, where he put forth a lot of these ideas. And the quote is, "Henceforth, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality."